Okay, for this lecture, I'm going to go over 6 problems for review on different parts of the course. This first question is about planes and lines, and we have a plane here, and we have 2 lines, L1 and L2, written in parametric form. And the first question for this is, explain why L1 does not intersect the plane. So we want to know if there's any point x, y, z on L1 that satisfies this equation. So we just go ahead and try these points in this equation and see what happens. So this is the plane, and I'm plugging in x equals 1 plus 2t, y equals 1 minus 2t, and z equals 3 plus t. And I'm trying to see what happens when I do that. And this is the equation we get. We can look at the value of t on the left-hand side. We'll have 6t from here, a minus 2t from here, so that's 4t total. And then minus 4t. So that'll give us 0 t's. And then we'll have 3 times 1 plus 1, that's 4, minus 12. So that's minus 8. And so this equation is the same as the equation minus 8 equals 7. So what does that mean? That means no matter what point I take on this first line, no matter what t I take for a point on this line, it's not going to satisfy this equation, because when I plug it in, I'm going to get minus 8 equals 7. So that's not true. So that means the line does not intersect the plane. They have no points in common. So let's look at the next question. Does L2 intersect the plane? Well, we want to do the same thing. We have to try a point on L2 given by these equations and put that into the plane. So in this equation for the plane, I get 3 times the x from here, the minus 1 plus t, plus the y, the 2 plus t, minus the 4z, which was minus 2 plus t. Check the t again, we'll have 3t, plus t is 4t, minus 4t. So those will all cancel again. We have minus 3 plus 2, so that's minus 1. And then plus 8, that's going to be 7. So when I simplify this expression, I'm just getting 7. And so this is just saying 7 equals 7. Well, it's certainly a true equation. What does that mean? Well, this means that no matter what t I take, no matter what point on this line that I'm looking at, it's going to satisfy this equation. So every point on this line is in fact on this plane because every point satisfies this equation. No matter what it is, it reduces to 7 equals 7. So the conclusion here is that, yes, the line intersects the plane because they have a point in common, but they really have every point in common that's on the line. I mean, the line is on the plane. So the next question, calculate the minimum distance from L1 to L2. Okay, so we have 2 lines here. We want to know the distance between them. One is on plane P and the other one is not, so they don't intersect. So what does this mean? Well, we can look and see if they're parallel. Let's see. For this line, the vector going in the direction of the line is 2, minus 2, 1. And for this line, the vector going in the direction is 1, 1, 1. So those vectors are not parallel. These 2 lines will not be parallel, so they're skew because they don't intersect as well. And so one is over the other one. So if we take L2 as on the plane and we're looking at L1, at some place, L1 is going to cross right over or right under L2. So at that particular point, the distance from that point to L2 would be the minimum distance, but that would also be the minimum distance from L1 to the plane P. So in other words, we want the distance from L1 to P. If I'm just looking at this L1, it's parallel to P, and there's one point where it's that minimum distance from L1 to L2, where L1's just right over L2 or right under L2, and that minimum distance is going to be the same as the minimum distance, or the only distance, from a point on L1 to P, the shortest distance from L1, any point on L1 to P. So I'm going to take a point on P, and I just got this point by looking at the equation P and just trying to figure out what would satisfy this. I noticed that 3 plus 4 is 7, so I went ahead and took 1 and minus 1 and then 0 for y. So that's where I got this point. You could have taken 3 here, that would give you a 9, and then 2 here would give you an 11, and then z equals to 1, that would give you 7. So you can pick x and y, basically anything you want, and then figure out what z has to be to make this true. So we got a point, 1, 0, minus 1 on the plane P. And now I want to take a point on the line L1 because we're trying to figure out the distance from L1 to P. L1, I took the usual point we would take when we just take t equal to 0. So we get a 1 here, and a 3 here. So 1, 1, 3 is on L1, and this is on P. So now the question is really, what's the distance from this point to P? So we started out wanting to know the distance between two lines, and now really what we're interested in is the distance from this point to P. Why is that? Because it doesn't make any difference what point you take on L1. L1's parallel to P, it doesn't intersect P. So any point on L1 is the same distance to P. So we're just going to take the point 1, 1, 3 and figure out the distance from that point to the plane P. This point comes into play because the way we figure out this distance is we take a vector going from this point, say, to this point. So that's a vector going from a point on the plane to the point 1, 1, 3 we're interested in. And we're going to look at the projection of that onto the normal vector to the plane P. And the length of that projection will give us the distance from 1, 1, 3 to the plane P. So the normal vector to the plane P is given by the coefficients of x, y, and z in this equation. We have 3, 1, and negative 4. So that's the normal to the plane. And this vector, I'm just going to call it u, is a vector going from this point to this point. So we have 1 minus 1 is 0, 1 minus 0 is 1, and 3 minus a negative 1 is 4. So that's a vector going from this point to this point. And what we want to do is project this vector onto the normal and find that length. So again, I'm just using one bar. For this particular problem, it came from an old course where we were using one bar instead of 2 bars for the length of a vector. But we have the length of the projection of u on to n here. And we want to know what is the length of that projection. So the formula is that we take the dot product of u and n in absolute value and then divide by the length of n. So the dot product, 0 times 3, 1 times 1, and 4 times negative 4. That's going to be negative 15. So in absolute value, this will give me 15. For the length of n, we have 9, 1, and 16 that we're adding together to get 26. And we want the square root of that. So we end up with 15 over the square root of 26. And that's the length of this projection. And that's the same thing then as a distance from this point 1, 1, 3 to this plane, which, as we said, is also the minimum distance from L1 to L2. So for C, this will be our answer. Let's look at the next question. Find the points on the graph of z equals x squared minus 3y squared minus 1, which are closest to the origin. Justify your answer. So how do we find the points on this graph that are closest to the origin? So let me describe that. First, we want to minimize this distance. So what is that distance we're trying to minimize? Well, we're talking about distance from a point to the origin. So if I call my point x, y, z, the distance is given by the square root of x squared plus y squared plus z squared. So I'm going to go ahead and use the square of this distance. If I minimize that, I'm minimizing the distance. So I'm looking at x squared plus y squared plus z squared. And we only want to consider x, y, z that satisfy this equation because we're trying to find the minimal distance from a point on this equation to 0, 0, 0. So what I'm going to do is to replace x squared with what this says. X squared is z plus 3y squared plus 1. You could have replaced z squared with what? Well, you would have x squared here plus y squared, and instead of z squared, you would have this squared. But notice that's a little bit more complicated than what I have here. I'm having the square of this over here, and that'd be a little bit more complicated. Or I could have replaced y squared with what is equal to up here if you solve for y squared, but that would be a fraction, and so it would be a little bit messier in this as well. So the reason I used x squared is because it's easy to see what x squared is, and it's something simple. So what I want to do then is to take this function and figure out where the minimum value of that occurs. So I've simplified here. I have a 3y squared and a y squared that's giving me 4y squared. I have a z squared, I have a z, and I have a 1. So this is the same as this function. I want to get the smallest value I can out of this and figure out at least where that is. And then I want to figure out what x is. And once I have the y and z that make this as small as possible, well, as long as I can get this equal to something squared, so if this is positive, then I can figure out this is something squared. That will tell you then the x, y, z that minimizes the distance from a point on here to here. Okay, so I'm making this as small as possible, then figure out what x is, and that'll give us what we want for that point. So to figure out the minimum value of this function and where it occurs, I'm just going to go ahead and set the partial derivatives equal to 0 here. Let's check the partial derivative of f with respect to y is just going to be 8y. So we get 8y there, and the partial derivative of f with respect to z, 2z plus 1. And I want both of these to be 0, so y is going to have to be 0, and z is going to have to be minus 1/2. So that's the only place where a minimum or maximum can occur for this, and so that's where I want to look. Now what happens to x? Again, x squared would equal this. So what's happening here is that we have y is 0 and z is minus 1/2. So we just have minus 1/2 plus 1, which gives us 1/2. So that means x is going to have to be plus or minus 1 over the square root of 2. The square root of 1/2, again with plus or minus. So we know what y and z are. So that gives us two possibilities for points that can give us either minimum or maximum. And then the question is, how do we differentiate? How do we know what's going on here? How do we finish off this problem? So we have 2 points to consider for this minimum or maximum. And the truth is that we're done already. So why is that enough? Well, we're trying to minimize this function. That's the square of the distance from x, y, z to the origin. And notice, no matter which of these 2 points we look at, because we're going to square the x, we're going to end up with the same value for this. So if there is a minimum, it has to be at both of these points. And there has to be a minimum because we're talking about the distance from a point on a surface to the origin. And if you just think about that, there has to be a point that's closest to the origin. And that minimum distance might be 0, but there's still a point that's closest to the origin someplace on this surface. So there is a minimum distance, and there's only one value where that minimum distance can have, because again, both of these gave us the same value for that distance. So this must be the points that are giving us that minimum distance, and they're both the same. So they're both giving us that minimum distance. And so our answer is just going to be both of these points. Next question, we want to calculate this limit. So the idea here is to realize that this is just the definition of the partial derivative of f with respect to y, where f in this case is e dxy. So to remind you, the definition of the partial derivative of f with respect to y would be you take f of x, y plus h, or you replace y with y plus h. You subtract f of x, y, that would be this, and then you divide that difference by h and see what happens as h goes to 0 in the limit. So this is just the definition again of this partial derivative. So we just calculate the partial derivative of this function with respect to y, treating x like a constant. We're going to get e to the xy times the derivative of xy with respect to y, which is x. And so we get x times e to the xy. And that's it. That's the answer to this question. Now, there is another way you could approach this problem, and that is to notice that when h equals 0, we have 0 in the denominator, but we also have 0 in the numerator. Since this limit only involves one variable that's changing, going to 0 here, we can use L'Hopital's rule by taking the derivative of the top and bottom with respect to h. So we're treating the h as the variable, and if you do that, you'll end up with the same answer. Let me go on to the next question. Calculate this limit as xy approaches the origin of x plus y squared divided by square root of x squared plus y squared. Or explain why the limit doesn't exist. And that's really what we're going to do. The limit doesn't exist. And really, in a question like this, the first thing to check is to approach the origin in a few different directions and see what happens. And that's what we're going to do. We're going to look in a couple directions here. And what directions you use can vary. I went ahead and used a positive x-axis to begin with. So I want to know what happens with this function when I look, what I'm calling f of xy here, when I look on the positive x-axis. So on the positive x-axis, y is 0. And so really this function just becomes f of x 0. And so we have x over the square root of x squared because the y is 0. And since x is positive in the positive x-axis, this is just going to be x, and we get x over x, which is 1. So on the positive x-axis, this function is 1. And I emphasize the positive x-axis here because the square root of x squared is not going to be x if we're on the negative x-axis. So for example, if x were negative 2, when you square that, you get 4 here. You take the square root, you get 2. 2 is not x. X was negative 2. In fact, 2 is negative x. So this is really the absolute value of x. And when x is positive, it's x. And when x is negative, it's minus x. So that's the idea for the rest of the argument. Then I'm just going to go ahead and look at what happens when we're on the negative x-axis. Again, y is 0, but now this is negative x. So I get x over negative x, and I get negative 1. So we have negative 1 on the negative x-axis. We have 1 on the positive x-axis. And so you can see the limit is 1 from one direction and negative 1 from the other. So as xy approaches the origin along the positive x-axis, where x is greater than 0, f of xy is just going to approach 1 because f is 1 there. And as xy approaches the origin along the negative x-axis, f of xy approaches negative 1. Now, I admit the word approaches is a little strange since it always equals 1 or minus 1, but that's what I mean there. The limit is going to equal 1 there, and the limit here is going to be negative 1. So we have two different values for the limit, and that means then the limit does not exist. So the value depends on how you approach the origin. Let's look at this next question. Here we have a function of 3 variables. F is a function of x, y, and z. And we're given a point that's on the graph f of x, y, z equals 0. You can look at that. 1 here, z is 0, so this is 0. 1 here, minus 2. So this point P satisfies this equation. And we want to calculate the directional derivative of f of x, y, z at the point P in the direction of this vector 6 minus 3, negative 2. Now, often when we've done directional derivative questions, we've had function of 2 variables. So this is something different. It's a function of 3 variables that we're doing the directional derivative of. But you do the same approach. The first thing is to calculate the gradient. The gradient of f, we take the derivatives with respect to x, y, and z. We get 2x for the derivative with respect to x. We're going to get 4yz plus 2y for the derivative with respect to y. And for the derivative with respect to z, we just have this term with z, and the derivative is going to be 2y squared with respect to z. So this is our gradient. Next, we want to know what that gradient is at p. So we plug in the point 1, 1, 0, and you can see if x is 1, this is 2. Here y is 1, but z is 0, so this is going to be 0. And then we have 2 times 1, so that's going to be 2. We have 2 times 1 squared, so this is going to be 2. So we just get the vector 2, 2, 2 for the gradient. Now, for the directional derivative, you also need a direction you're going in, which was given to us like this, but you want a unit vector giving that direction, so we should divide by the length of this. So the length of this vector, we have 36 plus 4 is 40, plus 9 is 49. The square root of that, 7. So the length of this vector is 7. We want it to have length 1, so we divide by 7 so that it has length 1. So this is our unit vector. It's 6 minus 3, 2 divided by 7. The directional derivative is defined as the dot product of these two vectors. So we want to take the dot product of the vector u, giving us the direction, and the gradient of f at the point we're interested in, 1, 1, 0. So taking the dot product, you can see we have 12, minus 6 is 6, minus 4 is 2, and then we have a 7 on the denominator here. So we're going to go ahead and get 2 7s. That's what we wanted. That's a directional derivative of f at the point 1, 1, 0 in the direction u, or if you want, this direction. So the answer is 2 7s. And the last question I want to look at for this lecture is to find an equation for the tangent plane to this surface at the point 3, minus 1, 2. Again, this point should satisfy this equation for this to make sense. 3 minus 1 is x plus y here. So we have 2 for 3 minus 1. And then 2 again plus z, which is 2. So this will be 4. So we have 2 times 4, which is 8. Z was 2. This is 2 times 2 squared. So this point is a point on this surface. Okay, so what we need for that is the gradient. But this gradient, we go ahead and take the 2z squared on the other side. And we get this function x plus y plus z minus the 2z squared equal to 0. So again, you take everything on one side, and your function is coming from with all those variables being on one side. So we want to take the gradient of this. Let me simplify, because we need derivatives, and I'm going to do x plus y times x plus y is x plus y squared, and then I have x plus y times z will give me xz plus yz, then minus 2z squared. I wrote it like this because it'll make it easier to take the derivative of x right here. Just give me twice x plus y, and so on. So I think it's a little bit easier to take derivatives this way. So when I compute the gradient, again, the derivative with respect to x will be twice x plus y from this part plus a z here. Derivative with respect to y, we get twice x plus y from this plus z. And then the derivative with respect to z, we have x plus y minus 4z. So that's our gradient. We're at a certain point, again, 3 minus 1, 2. So we plug in that point into our gradient. So x plus y is 2. So I'm getting 4 plus the z, which is 2. So that's giving me 6. No need to do the arithmetic again. These are the same. So this is 6. X plus y is still 2. Then I have minus 4 times 2, minus 8. So that's giving me a minus 6. And I factored out a 6 here. This is just 6 times 1, 1 minus 1 then. So this is the gradient, either one of these. So this vector will be perpendicular to the tangent plane that we want. That's what that gradient is doing for us. It's a normal to the tangent plane. But if this is perpendicular to the tangent plane, so is this vector, because they just differ by a constant, multiple here. So both of these will be normal to the tangent plane, and so I can use this as my normal. That makes it a little bit easier. I'm just going to have the coefficients for x, y, and z being 1, 1, minus 1. I need this equal to something. I want the point 3 minus 1, 2 to be on the plane. So we want to go ahead and plug in 3 for x, minus 1 for y, and 2 for z, and see what that equals. We're going to have 3, minus 1 is 2, minus 2 is 0. So this is going to equal 0. And again, the coefficients of x, y, and z came from this normal to the tangent plane. And the 0 here came in just by plugging in this point. So this is an equation then that represents the tangent plane we want. So that's the tangent plane to this surface at this point. And that finishes this problem and this lecture.